Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I want to talk about science and math. And today we are in AP Chemistry, and I have redone my units. So this is going to be a new playlist where it is in order of AP Classroom. The other list is in order of the Pearson Chemistry, the Central Science AP book. But this time I'm going to change it and do it with AP Classroom. So welcome, and let's get started. See, I told y'all it was hokey, but maybe I'll get merch. Welcome, welcome, welcome. And I always end it, science is great. So then I can have t-shirts that say science is great. I got 1,000 subscribers. They can all buy a t-shirt. You gotta work on my merch. Okay. I don't get any money from my YouTube channel, by the way. I've got the subscribers, but I don't have enough monthly views. So I'll probably never see a penny of it, which is really good because it might be considered a conflict of interest for me to be making money off of videos that I'm making while I'm at work. You see? So it's fine with me that I don't make any money in it. Okay, moles and molar mass. Okay, on the periodic table, the masses are those red numbers with decimals, right? So this is the decimals. The periodic table is its atomic mass, or I gotta hit draw, or AMU. Okay, you can calculate a molecule's formula mass by adding up. Oh, so also to this class, y'all don't be shy about the camera, about asking questions and stuff. Nobody knows who you are. It'll just be your voice. Don't worry about it. Don't be shy about being on the. Nobody watches these. It's not going viral. Nobody watches these except people who are taking AP Chemistry. So nobody's going to hear you. Okay, so here's an example. Sodium chloride. We look on the periodic table, and the red number under sodium is 22.99, and the number under chloride, if it's an ion, is 35.45, and you add them up and you get 58.44. AMUs. Okay, everybody remember that from honors? Yes. Okay, good. Okay, now this is not very useful because atoms are too small. We can't go get that, one sodium chloride. They're too little. Instead, we more often use in chemistry molar mass, which is often abbreviated MM. And it's why I have M&Ms on my periodic table. To remind you that if you need a molar mass, you need to look on the periodic table. Okay, and it is the same number, so that's convenient. But the units are grams per mole. Okay? And this is useful because the molar mass equals 1 mole, which equals Avogadro's number. Do y'all remember what Avogadro's number is? 6.023 Yes, you had it. It's 6.022. Sometimes you see it 6.023, like on our box over. That box over the sink is 1 mole of air. Okay? 6.022 times 10 to the 23rd of anything. So mole is a number that is like a dozen. You can have a dozen eggs, but you could also have a dozen Nintendo games. You can have a dozen of anything. Pair is what we measure socks in. It means 2, but you could also have a pair of chickens, whatever it is. Avogadro is the same thing. It's a number. We could have a mole of students, but of course we don't. I think it'd fill the whole world, but it is just this number of things. But if you have that number of atoms, then its mass is going to be the molar masses on the periodic table. So it's useful. It's the useful measurement we use in chemistry class. Okay? Now, since these are equal, you can use a conversion factor to switch between them. So we're going to do a little problem here. Now, it's just an example of a conversion factor problem, and I like to use train tracks for conversion factor problems. You can do them in steps and do each step going down in a column. You can use parentheses and an X for a time symbol, but I know I look like I'm straight out of college. but I'm not. And I've done this for decades. We're not going to talk about how many. And I've seen kids mess up problems by their parentheses becoming sixes and then them getting the wrong answer because of their messy parenthesis drawing. So I think it's better to use the train tracks. I'm also a member of this AP Chemistry Teachers Facebook group, and they discussed this recently, and all the teachers agreed that the train tracks are better, except one teacher who was trying to make all of her kids not do it with train tracks, and all the other teachers were all like, no, train tracks are better, and this is why. She was a new teacher. It was her first year doing AP. Okay, so here's an example. Now, whenever we do a word problem, we always start with our given, which is what I call what we know. And I like to have little hand signals to help you know what to do next. So if I ask you a question and you're staring at me with a blank look, I can say M&Ms, and you know to look at the periodic table. And if I say we start with what we, like this, you say no. Okay, this is your little memory trigger to always know you're on the AP test. You're panicking. You can't even remember your name, but suddenly you remember, oh yeah, we start with what we know. Okay, y'all do that a little bit better. One more time. We start with what we know. Very good. Okay, so we're going to write down 2 grams of neon. I'm not going to worry about the decimal right now. Now, then we draw our railroad tracks. What's written on top is in the numerator, what's in the bottom is in the denominator, and we want grams to cancel out, so we want it to go to the denominator, so we're going to push it, the units that are in the numerator down and over into the denominator, and this is more interesting if you give it sound effects. So I want grams of neon in the denominator, and I want to change that to mole, and how you change grams to mole is through the molar mass, and the molar mass of neon is 20 grams of neon, and I actually put 20.18, so I'm going to cram a little 18 in there, per 1 mole of neon. Now my grams of neon cancel out, so that's nice, but I still don't have what I want. I want particles and I've got moles, so I have to keep it going on my train tracks. Moles go to the denominator, and now I can write particles. Because I know the relationship. 1 mole is 6.022 times 10 to the 23rd particles. Moles cancel out, and I've got what I wanted, particles. And if your things cancel out to give you the right units, usually you're doing your math right. So that's called dimensional analysis. It's really handy in physics to make sure that you're getting the right thing. All right, so we multiply everything on top, 2 times 6.022 times 10 to the 23rd, enter, divide by the bottom, 20.18, and we get 5.968 times 10 to the 22nd. I want everybody to try that right now on your calculator. See if you remember how to put in a scientific notation. It's your button that says EE or EXP. See if you get that. And then we're going to talk about sig figs or sig digs. You are not the only one who's felt that way. And we're going to talk about that. So significant figures are a way of not over-representing the precision of your answer. You don't want your answer to look better than it is. Okay, did y'all get it? Okay, so let's talk about sig figs. How many significant figures are in 2.0 grams of neon, are given? How many? Zeros after the decimal count, so it's 2. Okay, so this is 2. So my answer should have 2. So what should I round this to? 6.0 times 10 to the 22nd. And then this is particles. We should always put a unit. and we gotta put a box around it. I used to teach bad kids in Cobb County, and they would work a problem every way you could. They'd add it, they'd subtract it, they'd multiply it and divide it, and not pick an answer, and it was a way of cheating. I know you good Paulding County kids would never think of that, but that's how they would do it. So you have to decide on an answer. Now, let me tell you, our goal in this class is not just to learn chemistry. Our goal in this class is to pass the AP test. So I have talked to some people who grade the AP test, and they said if you don't do significant figures, they take off 1 point 1 time. So if you don't remember to do significant figures, this is not going to fail you. They don't take off every time. They just take off 1 point. Now, we want all the points. So we want to remember significant figures, but if we don't, we're not going to beat ourselves up about it either. Okay, so that's nice to know, isn't it? Now, in college, you might get more of a punishment, but the AP test doesn't really punish you. Okay, mass spectronomy of elements. I was saying the wrong word. Okay, the mass of an atom is the number of protons plus the number of neutrons. Sometimes you see a whole number. Why? So like right here, I've got a Bohr model, and I've got 5 protons and 6 neutrons, so the mass of this element is 11. Why is it on the periodic table over there that those are all decimals and not something nice like 11?
Because those are approximates of how much they weigh.
Yes, but you need to tell me more. Correct, but I need more. Yes?
Is it because the electrons also have weight, but it's not nearly enough?
That is an excellent idea. If you didn't hear, he said that, is it because of the weight of the electrons? But that's not it. Remember, the electrons are so little, they can almost be thought of as light. Light doesn't have a weight, but that was a great idea. Yes?
The same atoms have a different number of neutrons, so the average all those together.
Yes. So that's half of it, but you're actually going to learn something new too. So the first reason why they're decimals is because there are different isotopes, different atoms who have different numbers of neutrons. I could have this one with 6, I could take one away and now it's got 5, but it has the same number of protons, so it's the same atom. Okay, so if we average their abundance, then we can get that weighted average, and that's the decimal. But there's actually one more reason. Does anybody know what it is? Okay, it is this. E equals mc squared. Have you heard of that? Very famous. And what it means is there is a relationship between energy and mass, and that they can be converted from one to the other. It's called binding energy. So in an atom, you know, opposites attract. So the electrons are attracted to that positive nucleus. But if you look at the nucleus over here, it's all positives. Why doesn't it explode in a force of repulsion? Because likes repel. Well, there's a thing called the strong force that holds them together with binding energy. It's one of the fundamental forces of nature, and it holds it all together, and it's very strong. But this big energy holding this together causes some of the mass to get converted to energy. So sometimes when you do problems about percent composition in college, it will tell you the masses of the different isotopes, and instead of those being whole numbers, they'll be decimals, and the reason why is part of the mass is getting converted to energy because of E equals mc squared. Now, don't you feel smart talking about E equals mc squared in your science class? You should. And understanding it a little bit. Okay, so there's a thing called a mass spectrometer. It's a machine that tells us the masses of atoms present by a graph called a mass spectrum. Okay, so this is brand new. Aren't you excited getting to learn something new? This is something that will definitely be on the AP test. This is part of our AP learning objectives, and there will at least be some multiple choice questions on this. And it's not hard, so let's learn it now. Okay, so here we have this graph, and it shows us that we have 2 isotopes of this atom. 35, one has a mass of 35, and one has a mass of 37. So the first thing it tells us is that there are 2 peaks in our graph, so we have 2 isotopes. 2 peaks equals 2 isotopes. Now, the next thing it tells us is it tells us the atomic mass of each. Of each isotope. So that, we'll go ahead and draw a line, is those numbers down there. 2 peaks, so we know that there are 2 isotopes. And the last thing it tells us is the relative amount of each. So which one has more naturally occurring isotopes? Isotope number 35 or 37? 35, because you can see that its peak is 3 times as big as the first peak. So if we were going to tell the percent composition of this element, what percent would 3 times as much translate to? 75%. So we have 75% isotope 35 and 25% isotope 37. Do we feel good about that? So now look on the periodic table. What element do you figure that is? Which one's close to between 35 and 37? Chlorine. Do you see it? So that's another question they could ask us about this. Okay, so here's another question they could ask us. Okay, so the average mass is the summation, which it means the abundance of one element times its mass. That's what we sort of did. So here's an example. If we looked at this, since we have 3 times as much 35 as 37, will the mass be closer to 35 or 37? 35, because we got more of it, right? And is it going to be 35? No, it's got to be a little more. Is it going to be under 35? No, can't be under 35. So these are questions that they're going to give you on the AP test like that. Okay, elemental compositions of pure substances. This is something you learned in honors, so this should be easy. A nice little review. Sometimes it's useful to know the composition in terms of the percent of elements in a compound. So here's an example problem. Carvone, C10H14O, causes the smell of spearmint oil. So there's my little spearmint leaves. Calculate the percent composition of carvone. So what you do is you list what you've got in it, then you tell how many by looking at the subscripts. So how many carbons do we have? 10. How many hydrogens? 14. And how many oxygens? 1. It's an understood 1. Then we multiply it times its molar mass off the periodic table. I'm just going to round to whole numbers for sake of ease here. So the molar mass of carbon rounds off to 12, hydrogen 1, and oxygen 16. Everybody cool with that? Of how I did that? Okay. All right, next. We multiply. 10 times 12 is 120. 14 times 1 is 14. 1 times 16 is 16. And then we add them up to get the total mass. Now, we want to find out the percent of each one, so we divide the mass of each one by the total mass times 100. So this is 120 times 150 times 100, and that ends up being about 80%. Then we do 14 divided by 150, and that ends up being about 9.3%. And then we are going to do 16 divided by 150 times 100, and that's about 10.6%. And this is the answer to the problem. Now you can check it. It should add up to be around 100, and it does. 100 is not the answer. The answer is the percent of each isotope or each element, whatever we're doing. Okay? Feel good about this? Okay, keep it going. Okay, sometimes you can calculate the empirical formula, the simplified smallest ratio from percent composition. So what's empirical formula? If I had C6H12O6, sugar. you notice that all of these subscripts have something that can be divided into them, a 6. So we could reduce this formula and it's C, oops, gotta keep my sleeve out of the way, H2O. That is the empirical formula. It's a reduced formula. It's if there's a number you can divide into all the subscripts you do. Now, is it the real formula? No. The real formula is that one. But sometimes it's useful in research to get the empirical formula, and then from that empirical formula you can get the molecular formula. Okay. It's not real, but it's useful to get something real. All right, for example, you have a sample that is 5.98% hydrogen and 94.2% oxygen. What is this empirical formula? So what you do is if they give you percents, you just list them as grams. If they give you grams, you just list it as grams. No matter what, you write it down as grams. The reason why is because any size sample has the same formula. If I have a teaspoon of water, it's H2O. If I have the ocean of water, it's H2O. And since I can have any size, I'm going to assume that it's 100 grams. If that doesn't make sense, don't worry. It's not important. It's just why we get to write grams. Okay? So you take these, and then for each one, I want to convert them to moles. So I'm going to use my little train tracks. I put grams on the bottom, moles on top, and I look up the molar mass off the periodic table, and it's 1 gram per 1 mole. And for oxygen, it's 16 grams for 1 mole. And then I write down the answer. And this one is 5.98 moles. And this one is 5.88 moles. Then I ask myself, which is smallest? Well, that one is smallest. So I'm going to divide them each by that. So for hydrogen, it's 5.98 divided by 5.88. And for oxygen, it is 5.88 divided by 5.88. And the answer you're looking for is one that can be rounded easily to a whole number. And both of these are ones. Yay! Now, if they're not, if it comes out 1.5, then you multiply everything by 2 to make them be whole numbers. You get a multiplier. Okay, so these subscripts are your subscripts. So for our empirical formula, it's HO. Ho, ho, ho. Now, that is our empirical formula, but sometimes then you take that and you get the real formula or the molecular formula. So what you do is you have to first calculate the empirical formula molar mass. So we have 1 hydrogen plus 1 oxygen, which is 16. That equals 17 grams per mole. Everybody understand how I got that mass of the empirical formula? I looked on the periodic table. 1 for hydrogen, 16 for oxygen. I added them up. Okay, next, then you divide this into the given molar mass. Notice I have a problem with a given molar mass. So I'm going to do 34 divided by 17, and that equals 2. So that is what I multiplied the subscripts of my empirical formula by. That's an understood 1. So 2 times 1 is 2, and 2 times 1 is 2. Dun, 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 it was peroxide, H2O2. Good? All right. Sometimes formulas can have water in the crystals. In our lab, in honors, we had some pretty blue crystals, copper sulfate. We heated them up, they turned gray because we evaporated all the water out of them. And then we added water back and they turned pretty blue again. Do y'all remember that? Who had me? I don't know if y'all did it in corn or not. Okay, so how you write this formula is you write the formula of the copper 2 sulfate, CuSO4, and then you do a dot for times, and then you write how many water molecules are bound up in the crystal, and there's 5, and then you write H2O. So there's some water in that crystal. Okay, still doing good? Nothing too bad so far? Okay, next, compositions of mixtures. So, if something is a compound, it has chemical bonds between the elements, and the compound does not have the same characteristics as the elements that make them up. For example, water. Water is made out of hydrogen gas, which is explosive, and oxygen gas, which is flammable, and both are gases at room temperature, but water is a liquid at room temperature and is neither explosive nor flammable, right? Mixtures do not have chemical bonds between the atoms, and it retains the properties of what's in the mixture. My favorite mixture is chocolate milk, and you can add 1 scoop of chocolate per cup of milk, or you could add 4 and make it really good. Put a lot of Nestle's Quick in it. They're both chocolate milk, but they don't have the same ratio of chocolate to milk, but you can still taste the chocolate in the milk, right? So keep that in your head. So mixtures don't. They don't have definite proportions. And you can have homogeneous or heterogeneous. Does homo mean same or different? Same. So a homogeneous or homogeneous mixture is the same throughout. And an example is homogenized milk. Not milk off the farm. It's got cream on top. But homogenized milk. Milk is the same through the whole thing. Heterogeneous means different. It's different in different parts. And you can think of that as Italian salad dressing that's got the oil on top and the vinegar on bottom and you have to shake it. That would be heterogeneous. Now, we spend a lot of time in research chemistry separating chemicals, and there's different ways you can do it. One way is to filter it. You use a piece of filter paper, you pour it through the filter paper, you end up with the liquid underneath and the stuff you filtered out on top, separated. There's a way in honors, well, we didn't do it in honors, but in AP or college chemistry where you can filter really fast. What you do is you use the sink and you get the sink going. And remember how we learned Bernoulli's principle that a fluid moving fast has a low pressure, not a high one? So you get that water going, you put a hose on it, and it causes a vacuum, and you can suck that liquid through that filter paper really fast. I have some of the funnels that will do that in the back, but we don't have the little apparatus on the sink. Maybe I could try to get some. When I got this room 4 years ago, they had those on the sink, but they didn't work. They were completely clogged with corrosion, and I couldn't get them uncorroded. So we might have to watch a video on it, but it's really cool. Fast filtering. Another way is distillation. With distillation, you have a mixture of things, and you heat it up, but those things evaporate at different temperatures. Like how you know alcohol evaporates sooner than water, right? Feels cold on your skin. Well, you put it in a flask and you heat it up, and whatever evaporates first comes off as a vapor. You put the vapor through a tube with water going through to cool it and condense it, and then it will drip into another beaker, and it's all purified then. It's called distillation. It's how they make alcohol. You've heard of that before. How they'll get the alcohol off of what they're making it from. There's another one called chromatography. Now, this was an AP question on the test last year, and I did not teach it to the kids. And I was like, rats, it was so easy. And that's one of the reasons why I decided to go by the AP, to switch to going by the AP units instead of the book. Because I taught through the book and we didn't hit this, and then it was on the test. And so the kids were coming to me afterwards going, there was this question about this. I'm like, rats. That would have been so easy for them to have gotten right, but they got it wrong because I didn't teach it to them. But just think, if they ask it again next year, you're going to be ready. Okay, so how chromatography works is a way of separating. It can be on a paper. We're going to do a little lab with it just to make sure y'all know it, where you do paper chromatography. You can also use a column, but you got something like paper. And you put the chemical on it, and then you have some sort of liquid that gets sucked up through the paper. And when it does, the heavy stuff stays down and the lighter stuff goes up. And then like you could cut it in between the two and run a solvent over it, and you could get it back down into two different beakers. Do you see that? Now I think Miss Corns, oh, that might have been AP. She was doing this with one of her biology classes. She was showing how to do this. But anybody do it with corn? Anybody do chromatography? So my son Nathan, who's doing research at Georgia Tech, getting his PhD, he has to run a lot of columns, is how they say it. They don't say, I'm going to separate something through chromatography. They say, I got to go run a column. And it's how he finds out if what he is making is, he gets it, his way he purifies it and then tests it to see what he made. So I'm always hearing about what column he ran. Okay, so we're going to do a lab with that. A centrifuge is you spin things to separate it. So before I started off as a chem major, and I did not like being quiet in the lab all the time, and I thought, this is not for me. So then I switched to a biochem major, and I was going to go into medicine. And so I got a job, and it was an internship in a lab at a hospital in South Carolina. And one of the things I had to do was I would get samples of blood and I would have to separate it and test it. So I would put the blood in this little machine in test tubes and turn it on, and it spins it real fast like your washing machine. And then all the heavy like red cells go to the bottom, then the white cells, and then you've got just the straw colored liquid part of your blood, the plasma, and then I could suck it out with a pipette and run different tests on it. I hated it. You get there, I had to get there at 5 o'clock. Nobody's happy to see you at 5 o'clock in the morning, turning on their lights at the hospital with needles to get their blood. So you're starting off your day with a lot of people really, really mad at you. Then you go to the lab and it's all quiet, and I don't like quiet. I like talking. And so I used to talk to my test tubes. And I'd say, okay, Mr. Smith, let's see how you're doing. We're going to put you in the centrifuge machine and we're going to spin you. Now I'm running my test, and now I put it in the computer. I'm like, oh, Mr. Smith, you're doing terrible. And then I look, I was like, oh, Mr. Smith is deceased. Well, yeah, we ran that test too late. Okay, let's go do something else. And then you had to have all your tests run by 8 o'clock because that's when the doctors got there to look. They didn't really, but all the information had to be in the computer by 8 o'clock. And then at 9 o'clock, we got to go eat free breakfast at the hospital cafeteria, and it was terrific. They had great food. I don't know about hospital food, but this Abbeville, South Carolina hospital had wonderful food. And one day I thought, you know, this is my favorite part of the job, is the free breakfast, sitting here eating it with my coworkers. And that is not a good career when the favorite part of the job is not doing the job, but eating breakfast. So then I thought, I got to do something else. So then I got into physical therapy, ended up hating it. And then my mom was like, well, you've had all that science and math. How about you be a teacher? And I was like, a teacher? Teachers don't make any money. I want money. And but then I decided to do it. And I've loved it ever since, but I was right. You don't make a lot of money, but I have a great fun job. And I use centrifuges in the lab in Abbeville, South Carolina. Okay, so we'll do a little lab with that. Okay, the next thing you should know already too, this is from Honors Chem, and this is atomic structure and electron configuration. So, you know, over here I've got a Bohr model, and it looks like the electrons all hang out in little circles around the atom. But in reality, only some of them do. The ones that are in the s orbitals that look like spheres. There's also p orbitals, and the books say they look like dumbbells. I lift weights. That doesn't look like a dumbbell. Okay, and then the d orbital, I think, looks like fat pluses. And then the f orbital, I say looks like fuzzies because there's so many of them, they just look kind of like an asterisk or something. Okay, so you need to know what your orbitals look like. And then the orbitals, there's only one kind of s orbital because, you know, all spheres have the same orientation. All spheres are alike. Remember learning that in geometry class? Remember that part of geometry? So, but the dumbbells can be on the x, y, or z axes. So there are 3 orientations of the p orbital. The d orbital looks like a fat plus, and it could be on the x and the y, or it could be between the x and the y, or it could be on the y and z, or it could be between the y and z, Or there's one that looks like two baby pacifiers stuck together that doesn't even look like a plus. So there are 5D orbital orientations, and then F there's a whole bunch because there's so many of them. Okay, so there are 7 different orbitals there. Okay, next, Coulomb's law. So we're going to talk a little bit about this. So there's a thing, and I think it is on your AP reference sheet, but this is the formula. And it is, Coulomb's law is used to calculate the force of attraction between or repulsion between charged particles. So this is the formula, Fe equals K. That K is kind of optional. When you learn, did you learn inverse and direct proportions in math class? Where X can be Y equals X. So if Y goes up, X goes up. If Y goes down, X goes down. Or Y equals 1 over X. If Y goes up, X goes down. And if X goes up, Y goes down. Opposite. You can either teach it where it's just Y equals X or Y equals 1 over X. Or sometimes they'll have a K in it, meaning it doesn't have to be 1. It could be some other number in there. It's a constant. This is the same thing. And I think on your AP sheet, it doesn't have the K, but the K is not important. The reason why they put the K in there is for the algebra part of teaching conic sections. Have y'all got there yet? I think y'all don't learn it. I used to teach it in Algebra 2, but I think y'all don't learn it at this school till pre-calculus. So, but anyway, just know, don't worry if that K is there or not. What this is saying is that the force is proportional to the size of the charge. Bigger charges, bigger force, and related to the distance. This is like a radius between these, and the further apart they are, the less force there is between them. So it's directly proportional to the charge and inversely proportional to the distance between the particles. Okay? Something new. It's fun to learn something new, right? Okay, so here is a question. Which experiences a greater force of attraction between the nucleus and the valence electrons? We're also going to talk about Coulomb's law as when we talk about different atoms, force of attraction between them. But right now we're talking about the nucleus and the electrons. So use Coulomb's law to explain. So look at the next one. So which one is going to have a greater force of attraction between the nucleus and the electrons? Magnesium or sodium, and why? Why do you think? Anybody got a guess? Don't be afraid to be wrong. It's good to be wrong. You'll learn when you're wrong. What? Guess one. Magnesium or sodium? If I tell you, do you think you can tell me why? Okay, so look at them. Magnesium and sodium are on the same level. Which one is bigger, sodium or magnesium? Magnesium. So which one has more charge, magnesium or sodium? Magnesium. So the answer is magnesium, and the reason why is it's got more charge, bigger Q's, but the radius, the R stays the same because they're both on level 3. The electrons are on level 3, the same distance from the nucleus. Can you imagine that? So that would be how we could explain that with Coulomb's law. Now what about sodium or potassium? Sodium is on top of potassium. So which one do you think is going to have more charge? Okay, it is sodium, and the reason why is they have the same valence electrons, like they're both in the s orbitals, but sodium has a smaller distance from the nucleus to the electrons, so it's stronger. It's like when you get a magnet close to metal, the closer you get, the greater that force is, right? You can feel it. So those electrons are closer to the nucleus, so it's got more force. We'll practice, you'll get better at it. I can see some of y'all are not real happy with this new idea in your life, but we'll practice, you'll get better. Okay, next. So there are patterns on the periodic table that help you write the electron configuration of an atom or an ion. So hopefully you learned this in honors. When you write electron configurations, and that's how the electrons fill an atom, you have to follow 3 rules. The first one is the off-ball principle, which is the lowest energy level fills first. We have turtles, because you know they're not going to want, they're lazy and slow. They're not going to want to go bouncing up high into the atom. The next one is Hund's rule. Everybody gets a room by themselves before they pair up, or I'm going to say double up. Okay, and the last one is Pauli's exclusion principle. No 2 electrons have the same 4 quantum numbers. For example, oxygen. We're going to do oxygen's electron configuration. Anybody want to do it for me? Anybody remember? Yes, Ella, give it to me. 1s what? 1s2, that's right, good job. 2s2. 2p4, yay, Ella did it. Okay, so let's talk about how to do this. Sorry, YouTube, I'm going to walk over to the periodic table, so you'll just have to listen. Okay, I told you my production value is going way down. I'll wander out of the shot all the time. Okay, so let's do another one. Let's do gold. Okay, you ready? So how you do is you just go back and forth on the periodic table, following these little cues. This is the S block, D block, P block, F block. So we're going to go do this until I get to gold. It's going to start with 1s, and we pretend like helium is right there, 1s2. Then 2s2, 2p6, 3s2, 3p6, 4s2, 3, it drops down 1, so I'll put a 3 on my periodic table. 3d10. Now we're back to 4. 4p6. 5s2. 4d10. 5p6. 6s2. And this little LA is telling you go down here next. 4f14. Now it says LU to tell you go back up here. So now it's 5D, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now that's a lot to write down. So there's a noble gas shortcut. You go back to the noble gas before it, you put it in square brackets and say, same as xenon except 6s2, 4f14, 5d9. Everybody remember that? Good. Good job. Okay, sometimes you have to do orbital diagrams where you draw arrows to represent the atoms. In an orbital, you go up before you go back and go down. So we're going to do oxygen. Oh, this was supposed to be fluorine. I did oxygen in the other class. Okay, so let's do fluorine. Go over there. It's 1s2, so you draw an arrow up and an arrow down to represent those. Then it's 2s2. Now 2p, we've got 5 of them. Do you see how it's 5 squares from boron to fluorine? So we go up, up, up for the first 3, and the last 2 we go down, down. And then here's one you can practice on your own, the orbital diagram for chromium. Okay, I got the little thing here for you to practice here. We're not going to take the time right now. You can practice that later. I think y'all remember that pretty good. Okay, so you can excite electrons. Not buying them tickets to their favorite concert. Nope. We excite them by burning them in fire, flame test. We excite them with electricity, neon signs. We excited them with light, like in glow in the dark. We excited them with mechanical force when we crushed lifesavers and made them spark. And we excited them with chemicals when we got out glow sticks. That's a light lab my class did. I'm not sure that Corn does all of it. I know Weeks does some of it. I know she does the glow sticks, right? So you can excite them. There's our little candle for exciting it. An excited electron configuration refers to a situation where at least one of the electrons moved up to a higher energy level. Electron configuration of ions. When electrons are removed from an atom to form a cation, so over there by the cats, that's why there's cats on the wall. So like sodium, if it's going to lose an electron, it is going to remove it first from the orbital having, let me make sure I'm going to this, the highest principal quantum number in energy. So what that's saying is, if sodium is going to lose one, it's going to lose that one on the third level. Okay, it's not going to lose. It's going to lose a valence electron, the one that's on the highest level. When an atom of a transition metal, so do y'all remember what the transition metals are? It's the ones that are in this rectangle right here. These are our hippies, our metals who let their electrons run wild and free. They're shiny, they can get electricity. Okay, so if they are going to lose one, then they are going to lose, before they lose any of their d orbitals, they lose something that is their s orbitals first. If additional electrons are lost, once all the s ones are gone, then they'll come out of the d orbitals. So it's just a little thing to think about. Next, quantum numbers. Okay, so every electron has an address of 4 numbers so we can know which electron we're talking about. And just like how every person in the world has a different address, every electron has a different set of 4 quantum numbers. And the first one is called the principal quantum number. Its symbol is N, and it tells which level it's on. 1, 2, 3, 4, 5, 6, 7. The next one is the angular momentum quantum number. Its symbol is L, and it's a number that tells you the shape of the orbital. S orbitals are 0, and that's easy because they're spheres, and zeros look like spheres. P orbitals are 1. D orbitals are 2, and F orbitals are 3. The third quantum number is called the magnetic quantum number. Don't know why. It is M sub L, and that L is usually written in cursive. Once again, don't know why, but it is a number that tells you which orbital it is of the orbitals. Okay, so S, there's only one S, okay, and it's a sphere, so it is always 0. S is, if it's an S orbital, that third number is going to be 0. If it is, so we'll put S over here. If it's P, there's 3 different orbitals it can be. It could be X, Y, or Z, right? So the first electron, we go into the first square, and it, so this one's always 0. It is -1, 0, 1 is how they differentiate between the 3 p orbitals. The first, so like, if you were putting an electron into boron, that electron's quantum number is going to be -1 because it's going into the first one. Carbon's last electron would go into 0. And nitrogen, its last electron would go into 1. But then oxygen, now we're doubling up, its last electron is going to go into -1. Okay? And then D, you always do this same pattern. D's got 5. You put 0 in the middle, -1 on one side, +1 on the other, -2 on one side, -3 on the other. So that tells you your D's. And then your F, you do the same thing one more time. Oh, I said -3. -2. -2 on the other. And then F, you've got 7. 1, 2, 3, 4, 5, 6, 7. 0 goes in the middle. -1, 1. -2, 2. -3, 3. And that's, oh, and then the last one, when you put in the arrows, you know, you go up first and down second. Up is plus a half, and down is minus a half. It's showing the difference between the one going clockwise and the one rotating counterclockwise. Now, we did not have Maxwell's back. Come in. You're missing notes, but
I
don't
know.
worry. We're videotaping it for YouTube. So you'll be able to get all caught up. Pick up the papers over there. Also, Maxwell, get one of these books, and you're going to write your number next to your name on the roll. On here. So find your name on this list and write your book number on it and initial it. Pick one of these books, and the numbers are on the bottom. And then you're going to take that home. And you're going to leave it at home. It's going to be your home book. You're going to have another book you can use here at class, so you don't have to carry that big, heavy book around. All right. We okay on the quantum numbers? If you're not, there's some more videos on my YouTube channel that explain it for Honors Chem too. Okay, the next thing you're going to get to learn something new. Yay! Photoelectron spectroscopy. Hasn't so much of these notes been reviewed? Aren't you starting to feel really confident about AP Chem now that so much of it's reviewed? Okay, but this is new. So the energies of electrons in a given shell can be measured experimental with photoelectron spectroscopy, which is abbreviated PES, because we're nerds and we like little abbreviations in science. Okay, and it shows the binding energy, capital E is energy, for each subshell. And it shows the number of electrons in each subshell. So this is another question I guarantee you will have on the AP exam. It will probably be a multiple choice question where you're going to be given a little thing, you're going to be given a little graph, and you have to answer questions on it. Okay, so what this graph represents is the electrons in the atom. It represents 1s2, 2s2, and then comes 2p6. That's the song about electron configuration. It goes, electron configuration, just they're really slick. Okay, so now we're got the singing out of our system. All right, so this represents one of these, and we can figure out what atom it is by looking at this. Now, this is the tricky part. Sometimes it goes from left to right, where it goes 1s1, 1s2, 2p6, 3s2, 3p6, like that. But sometimes it goes the other way, and you have to look at it and figure it out. And I can tell this one goes the other way because, do you see how that goes 2? And that one goes 2? So that means that's 1s2, and that's 2s2, and that's 2p6, and that's 3s2, and that's 3p1. Can you see that from the relative sizes of those peaks?
Yeah.
Yes? Okay. So in this atom, it's got 2 in 1s. So this is 1s. It's got 2 in 2s. So that one's 2s. It's got 6 in 2p. That's 2p right there. It's got 2 in 3s. There's, oops, get my sleeve out of the way. 3s. And it's got 1 in 3p. That's 3p, and it's only got 1. So which atom would that be? That's 1s2 and 2s2, and then comes 2p6. And then it is 3s2 and 3p1. What is that? Aluminum! Somebody got it! Woo! Yay! Okay? Kind of getting it? So something fun, something new. All right, periodic trends. This is not new. It is old. So what do the elements want? They want to feel like what? You learned this in honors? They want to feel like a noble gas. They want to follow the octet rule and have 8 valence electrons. You remember this from honors? Oh, I gave away your seat, Maxwell. You might have noticed that. Noah got misplaced and didn't get to take honors. He had to take regular. So there are things he doesn't know because he hasn't ever been taught them. Remember all that stuff I said? This is for honors, but regular doesn't get it? Noah didn't get it. So I moved him up so I could keep an eye on him and I could see when he's getting lost. You made 100 in honors chemistry, right? So I figured you could learn further back. So you can pick any of those 3 seats on the row you're on right now to be your new seat. You can learn from anywhere in the room. I know you're smart enough to. Okay, and you already know honors chem really good. Okay, so this causes periodic trends. And the periodic trends are pretty easy to remember if you think of the electrons like children. Okay, so alkaline metals and alkaline earth metals over there by the cats, they want to lose electrons. They're like bad parents who like abandon their children at Walmart. I just saw that where a girl, where'd she abandon her kid? They just arrested her. If you take them to the fire department, they won't arrest you. They have a box you can leave a baby in and not get arrested. But someone just left one somewhere and got arrested. She didn't know about the fireman box.
May I use the restroom?
You cannot, because they are enforcing the 15-minute rule. And we're within the 15 minutes. Just barely. It won't let me. It won't let me do a Minga pass now. I'm sorry. Okay. The ones near the noble gases like chlorine and bromine, if they could just gain a few electrons, they would feel like a noble gas. So these are the bad people who try to steal someone else's baby. So, like that. The non-metals are the ones like carbon who want to work out sharing agreements. Because if you look at the periodic table, fluorine wants to get 1. Oxygen wants to get 2, and nitrogen wants to get 3. And if you look at the other side, sodium wants to lose 1, magnesium wants to lose 2, and aluminum wants to lose 3. Everybody remember that? But carbon's family is 4 from either side. It's too far. So it usually doesn't become ionic. Instead, it works out sharing agreement, covalent ones. So these are our divorced parents. They're going to share the little electrons. Now, the metals, in the transition metals, I say they're hippies because they did this thing where none of the electrons are really assigned to a nucleus, and they let the electrons just go freely wherever they want to in between them, like how hippie parents did in the 60s. They let their little electrons run wild and free. Okay? And all of this causes 4 things, but really it's 4 ways of saying the same thing. Electronegativity, ionization energy, shielding effect, and element size are all related to this. These are our periodic trends, okay? So electronegativity is the ability to attract electrons to oneself. Big E is energy, little e is electrons. So, if you think about it, those cations over there by the kitty cats, they don't want electrons. So they don't have much electronegativity. Fluorine, chlorine, and bromine, they want to keep theirs and steal yours. So they're going to have a high electronegativity. So the trends, we're going to draw them on the periodic table here. We'll start with orange. So for electronegativity, as the electrons go down, electronegativity decreases. As an atom gets more and more electrons, it has a harder time holding them close. And as you go across, electronegativity increases because they want their electrons more and more and more, and they're going to hold them tight. The second periodic trend, we'll make it blue, is ionization energy. It's the energy it takes to remove an electron. And as you go down a period, that decreases. Once an atom has a whole lot of electrons, it's pretty easy to steal one. But as you go across, the ionization energy increases. It's much harder to get one because they love theirs and they want to keep them. The next one is called shielding effect. Whoops. For shielding effect, we'll go with brown for shielding effect. Okay? Shielding effect is the power of the nucleus is reduced by electrons. So what that means is, that whole Coulomb's law, the nucleus exerts a power on the electrons, pulling them to themselves. But if there's a whole bunch of electrons in between the nucleus and a far out electron, that power is going to be reduced. So it's like little kids. If there's a whole bunch of little kids, if somebody's got 12 of them, you know some of those kids are getting away with stuff. But if a mom only has 1 or 2, they're much more likely to get punished if they do something wrong, right? Y'all seen it in big families if you've been around. So shielding effect, as you go down a period, it increases. There's more shielding effect. But as you go across, as they are going across and pulling them tighter, there's really no change. Triangle means change in science and math. It means change or difference. Okay? And then the last one, element size. This is a weird one. We'll make it purple. Okay. As you go across a period, the size gets smaller. The reason why is because they're holding them closer. So as you go down a column, it increases. They do get bigger. But as you go across, it decreases. They get smaller as they go across. And the AP chemistry test loves these questions. Which one has a higher shielding effect? Which one is bigger? Lots of multiple choice questions right there. Okay, how are we doing? We get out at 50 now, right? Let me check. Let me check the new bell schedule. It's at 42. 42. We only got a few minutes left. Let's try to finish this little bit. No. We're right here. Okay, we're going to stop right there. That's where I stopped in the other class too. So this video, we'll have to have a part 2. Come back for 1.8. We'll do that first tomorrow. Science is great.